calculus in astronomy. Now, astronomy is a science that deals with the material universe beyond Earth's atmosphere. Essentially, it's the study of space and all things therein, so if it's not on Earth and somebody is studying it, then said someone is doing astronomy. Astronomy is something of a blanket term that covers an enormous range of specialized topics, all of which rely heavily on physics, chemistry, or some combination thereof. Some fields or studies of specific aspects of astronomy include solar astronomy, planetary science, stellar astronomy, galactic astronomy, extragalactic astronomy, and cosmology. All of these fields look at some aspects of the universe, but on different scales. The number of specific fields that are covered by astronomy is actually pretty staggering. As for its use of calculus, when one considers that the universe is constantly changing, that the science upon which large portions of astronomy, or more specifically astrophysics, is based, relies heavily on mathematics, and that calculus is essentially, if not by definition, the mathematics of change, it follows that calculus would be an integral part of astronomy. Almost everything from the engineering involved in the creation of the devices necessary to do astrophysics to the mathematical models for the movement and behavior of various celestial bodies is, if not based on, at least relying to some extent on calculus. Rockets, radio telescopes, nebulae, black holes, orbits, supernovae, stars, galaxies, planets, etc., all of these things are changing in some way or another, and are all modelled with calculus, to some extent. In this short time, I'm going to attempt to present something of a spectrum of problems that require the use of calculus within the field of astrophysics, and by extension, some of the engineering required to do astrophysics. Now, before one can start making great astronomical discoveries, one must first be able to see the stars that one is studying. While optical lens telescopes are all well and good for stargazing, hardcore astronomers will want something bigger. With telescopes now being built with light-collecting surfaces more than 39 meters across, glass optical lenses become far too heavy and cumbersome to be practical. Instead, engineers use parabolic reflectors to focus parallel rays of light towards a single focal point. Now let's say that you've been given the required dimensions of a parabolic reflector and the dimensions of a spherical collector to be placed at the focal point. You're then asked to find the magnification index of such a setup that it would produce. Now, I won't go into great detail in this first part, in fact I'll skip over a lot of it, but that's mainly because it's not calculus and it's all fairly straightforward.
So, given the parabolic dish is 120 centimeters across and 18 centimeters deep, this means that if we were to graph this as a parabola with its center at the origin, it will pass through the points 60, 18, and negative 60, 18. Now, plugging that into our standard form for a parabola, we come up with our a constant in front of the x squared, and then we have our function for the parabola. Graph that looks like this, where the points b and a are the edges of our parabolic dish. Now, next we need to find focal length of the parabola. Now, in order to do that, we use the focal length formula. Now, there's a whole derivation behind this, but that's a whole other thing. So, we'll just use the formula for the moment, and that gives us a focal length of 50. So, that means that the focus is at the point 0, 50 on our plane, and there's plotted point C at the point 0, 50. Now, we have the spherical collector. This is the thing that the light will reflect from the parabolic dish onto, and that will collect it. So, representing sphere in 2 dimensions, we have a circle with its center at the origin. We use the standard form for a circle to do that. And then we want to define 2 lines joining the focal point with the edges of our parabola. Those are the last spots where light will be able to reflect off of our parabolic dish and onto the reflector. And what we're going to do is we're going to find where these lines intersect with this circle, and use that to find the area of a spherical cap. So that's what we're doing here. We're using that to find the area. So this is just finding the area that light will actually be reflected onto our spherical collector.
In order to find a magnification index, we need to find the surface area of our parabola, and then compare that to the surface area that light will be reflected onto the spheroid. So, the surface area formula is this integral here. Now, this part of the integral, everything under the square root, well, including the square root actually, is a arc length integral. It adds up all of the points along an arc to give you the length of an arc. And then integrating it by 2 pi x essentially takes that line and rotates it around the y-axis, giving you where this part of the integral gave you the length of the line. This part integrates all into a surface area. Now, the derivation is different to that, but that's essentially what it's getting at. Now, first we need to find dy dx in here, so we take the derivative of our original parabolic formula. That's quite straightforward. And then we take out 2 pi as a constant from the integrand, because we can do that, and then substitute in our dy dx in there. Now, that's not really something that we can integrate, so we're going to do some u substitution. So we let u equal the stuff that was under the square root here, and then we find du dx. Now, we need an x dx in order to replace these 2 terms here, so that we can get everything in terms of u. So we find that by using our derivative du dx, and then multiplying out gives us x dx equals 5,000 du, and then substituting those 2 values in, we have we have 5,000 root u du. Now, that's fairly easy to integrate. That's straightforward. I don't really need to go into that. And now, all-important constant on the end. And then we substitute back in our value for u. And finally, after some simplification, we get that the surface area is pi on 150 times the what's that? The square root of 1000 plus x squared cubed plus c. Now that's our indefinite integral. Now we want to take that and actually find some values for it. We want to integrate it from 0 to 60, because that's from the origin of the parabola to the edge of the parabola. So integrating from 0 to 60 comes through like this, working with our definite integral, and here is our final formula, our final value actually for the surface area of our parabola. Then we divide the area of the parabola by the area of the collector, and working that through, we find the value 4046.26. So this parabolic dish will magnify light coming into it by about 4,000 times, which is interesting. Now, this surface area calculation is useful for a number of applications. It could give the quantity of a coating to be applied to a dish, or help in calculating the mass of the dish, especially if it's being designed to be sent up into space, which actually brings us to our next application. Now, let's say you've designed yourself a telescope, but you want to get it up into space where it can take some lovely pictures. That way you don't have to deal with aberration from the atmosphere and such like. Now, of course, in order to get your telescope into space, you need a rocket. We want to make sure, however, that your precious telescope can withstand all of the forces of the flight, so without further ado, let's have a look at some applications of calculus in rocket science. So for starters, we're given two functions. We're given m of x, which is the mass of the rocket along its flight as it burns fuel. Of course, we have a decreasing function of x squared, so as it burns fuel, it'll get lighter, the mass will decrease. And the second gives thrust in relation to time. In both cases, x is the time in seconds. Using the formula F equals ma, we can use our function for mass and function for thrust in order to find a function a of x, which gives us the acceleration, which is what we're really most interested in, because we're looking at the forces that will be applied to our telescope and whether or not it'll be able to make the flight. Look at the acceleration curve, which is really our most important. Now, taking the derivative of our acceleration curve, we end up with this kind of messy function down here. Now we have our first obvious root, which is rather trivial, where x equals 0, but the other roots require you to solve a fourth order polynomial, which is, well, in some cases easy. In this particular case, it doesn't actually come out to any nice values. So we can solve this graphically and look at the x-intercepts here, and we find we have this point A here at, 4.56 seconds, where the acceleration is at a peak. That's our highest acceleration value anywhere on that curve, which means that we're interested in that point, because that's the point at which our payload is going to be under the most stress. So, plugging in our value, 4.56, into our acceleration formula, we get 2.849. Now, the units for acceleration in this are in Gs. So, 2.849, our equipment on board the rocket would be experiencing, or astronauts as well, 2.849 times, so nearly 3 times their standard weight on Earth. Let's say that you've designed, built, and flown your telescope into space, and now you've got it taking pictures of stars, galaxies, nebulae, and all kinds of things. What use could calculus possibly have now, you might ask? Well, an awful lot, actually. Now, while the pictures that modern telescopes are taking are extremely pretty to the majority of us, to astronomers they're 2D snapshots of something three-dimensional and active. They want to understand these things and attempt to model them mathematically so that we might better understand them. For instance, let's say that your telescope took a picture of this nebula, Able 38 it's called. Now, looking at this picture, and knowing a little something about nebulae, you might believe that this particular cloud is a hollow spherical shell with an almost uniform density of gas. However, being a good scientist, you need to be able to prove this with something more than your intuition. So you come up with a model and use calculus to help confirm or deny your hypothesis. So we want to calculate the intensity of the nebula, which is this grey shaded area here, at different radii, b, from its center, along a series of chords through the nebula. Here AB is one of these. One is an example of one such chord. Now, the intensity, which we'll call I of B, will be a function, will be proportional to the density of gas within the nebula, which we define as d of r, and I'll have those values up in a second. Now, because d of r will vary along this chord here, we have to sum up the contribution to the intensity from each spot along AB. So we need to sum up essentially all of these points along here. Now, let's just get into it. So, using the Pythagorean formula, L squared here is r squared minus b squared, and further, L equals the square root of r squared minus b squared. So we'll take our derivative of that, so of this formula up here, so 2L dl equals 2R dr. Now we're assuming that b here is a constant, because for any given chord, b will be constant, and r and L will vary along the chord. L will vary as a function of r. So dl equals, so taking out derivative, dl equals r dr on L, and then substituting in this value for L that we got here, dl equals r dr on the square root of r squared minus b squared. So we'll take this and integrate all of it to kind of sum everything up. So subbing in our dl, we get this function here, or derivative here, and what we want to do is we want to integrate it so that we can get our intensity as a function of b. Now, also, we're going to integrate from Ri to R0, because we're only interested in this grey area. We're not interested in this hollow area or anything outside. So that's going to be our definite integral. Now, the intensity. Okay, so where are we? Now, there's a few other assumptions that we have to make. That dr equals 0 from R equals 0 to Ri, so essentially we're saying that the density of gas in this hollow part in the middle is 0. There's no gas in there, which of course stands with it being hollow. And we're also assuming that the density inside this grey area is constant. So we can set dr to d0, so just d0 is some constant, which means that we can actually take out our d0 from our integrand and put it on the outside here, because we don't want that in there. Now, doing u substitution again, we let u equal r squared minus b squared, the stuff under the square root here. Du equals 2r dr. Okay, so we've derived our u. B, remember, is a constant for any given chord, so we keep B as a constant. Du equals 2r dr. So we want r dr on its own as a function of du, or related to du, so that we can have everything in here in terms of u. So we come up with this. Now, doing our integration now, we're going to ignore the definite part for the moment. We'll come back to that in a minute. So this is actually our indefinite integral down here. That's fairly straightforward. We end up with I of b equals d0 root u plus c, substituting back in, u equals r squared minus b squared. We get I of b equals d0 root r squared minus b squared plus c. Now, okay, taking a step back from the problem at this point, we need to remember that there are actually two halves to the shell. See, we're essentially only looking at a slice of the shell, or one face of the shell. But what's actually happening when, in this picture over here, when it was taken, if this is actually a spherical shell, there's a back and a front side to it, and when you see it, you kind of see them layered on top of each other. So what we actually have to do is we have to multiply both our halves. We have to multiply both parts of the definite integral by 2 in order to account for this both halves of the shell. Okay, coming back to this particular nebula, Able 38, we know that it's about 5 light years across, which means that R0, the distance from the radius from the center to the outer edge, is about 2.5 light years, and they also know that the distance from the center to the inner ring here is approximately 2.2 light years. Now, putting in those values for Ri and R0, we get these two equations. Now, why do we have two equations? There's an equation for when R is less than 2.2, which is just this center part in the middle here, and of course multiplied by 2, so we have the front and the back. And then there's also the second equation down here for when R is greater than 2.2, in which case we have both values. We get, plugging these two functions in, we get this really nice looking function here. And, okay, so this vertical axis here is for the intensity. It gives us arbitrary units of intensity. It's basically just showing us a scale of intensity. And what we see here is this much lower intensity in the middle, and then this huge spike of intensity on the outside. So it's much brighter in this ring on the outside. This is essentially looking at the nebula from side on, and you can see that that is pretty congruous with what we've got down here. This kind of vague brightness in the middle, and then this very bright ring around the outside. And so, using calculus, we've created a model for what this nebula possibly is. And yes, this model lends credence to the hypothesis that the nebula is a thin, spherical shell with a uniform density of gas in it. These few examples are but a drop in the ocean in comparison to all of the applications that calculus has in astronomy. And I hope that I've shown that in a wide range of stages and areas of astronomy, from the practical to the theoretical, calculus is an essential tool.